Okay, so I wanted to give a high-level description on some recent work that we've been doing. So we've been looking at so everyone knows about cloud and what it can do to provide kind of ad hoc scientific compute platforms on cloud infrastructure. But what we've been looking at is how do we then take this to the next level, and we've created like this miniature version, like a snow globe of our world, but how do we actually bring data from our home directories into that world? So how do we create a cloud resource which is actually part of our data sphere, as well as being out there on someone else's computer? I guess that cloud usually means someone else's computer, but can we also break down this thing of having it also being someone else's file system, which is a bit sucky? So I work for a company called Stack HPC. We've been going for a few years. We're quite small. You won't have heard of us unless you work in the same kind of business area. I founded this company with my colleague John Taylor. Back in 1992, we first worked together at Mako, and I've had the good fortune to work for a number of interesting and exciting and challenging companies since then, working on some cutting-edge technologies, some of which are actually also successful, but not all. So now we work on the convergence of cloud, high-performance computing, big data, AI. And so this new project is something which very much represents that convergence. So Mark referred in the opening keynote to the IRIS project on Passant, and this project is a program by the Science and Technologies Facilities Council. It provides a pooling of compute resources across many sites, and also a pooling of expertise as well. But the compute comes in three principal forms. So we have grid, so grid PP kind of workflows. We have batch scheduled HPC for tightly coupled sort of conventional HPC workloads. But then we have this third kind of area, which is private cloud, OpenStack private cloud in particular. And the idea there is about meeting all the kind of the non-traditional, the square pegs, the bits that don't really fit into grid and don't really fit into batch compute. So problems or platforms which are running inside of a Kubernetes environment, for example. We heard Glyn was referring to that earlier. The long tail use cases that can be defined in a software-defined infrastructure, but are hard to represent outside of that paradigm. You can also refer to them as the choose your own adventure brigade. And so we've got a nice example of one of those. IRIS and the OpenStack projects within it are collaborating together to create some sort of cross-site portability for cloud. So what we're looking at here, we're creating this thing which is being referred to internally as sort of scientific OpenStack, as an analogy to scientific Linux, in that we provide a few of the core components to make working from one cloud to another a little bit more user-friendly, a little bit less of the avoidable pain in the backside that it usually can be. So some of those capabilities are things like federated AAI. So we're looking at single sign-on for the IRIS OpenStack clouds. I log in using my Gmail account to OpenStack, where the sites support it. Also, other cutting-edge technologies for private cloud are things like preemptible instances. So how do we gain utilization by making use of things like the AWS Spot market? Having said all that, IRIS is not providing essentially a sort of a research equivalent to the AWS or Azure experience. It's not self-service in the sense that you don't just turn up and ask, make a VM and go and use it. Cloud resources are still allocated as a as an allocation, as by requesting resources from the resource allocation board. So there's still this sort of very much a priori, I request from my scientific project these particular resources. That is then considered in the weight of all others, and an allocation is granted for a time. But then we get access to the OpenStack APIs, so we get to do this self-service experience within the quota set to our project. And if we don't use it, the idea is then that opportunistic usage will come along and use the resources if we aren't making use of them ourselves. And that gives us really these sort of three advantages, three delights, I think of it as. We get planned consumption, so we can ask in advance, I need this particular research project, needs this particular amount of compute, and they will have it allocated or guaranteed to them, which is a very uncloudy thing. We then get to software define and self-serve in the way that cloud infrastructure works so well. But then we also get 100% or close to 100% utilization of the resources, because anything we don't get used gets picked up by the parasites, who will then create preemptible instances on the stuff while we're not using it. So, yes. Sorry. All right, not parasites. Wrong analogy. So, actually, if we want to make scientific compute platforms in the cloud, it's actually pretty simple, because cloud native is this idea of codifying the processes of system administration as one component of it. So then we can, once we've talked to the infrastructure APIs to make the machines, we can just follow these processes, these codified processes, using cloud methods, tools very much like Ansible, for example, in order to take a bunch of raw machines and pave them with a platform, a Slurm workload manager, or other such things. But we can actually then bring in a combination in this cloud environment, and we can use conventional interfaces and familiar working environments like Slurm, but at the same time we can back those with cloud native components and technologies like Seth storage, Prometheus for telemetry and performance analytics, those kinds of things, and bring together something which is representative of the best of both worlds. So I'm going to skip over this because we are a little tight on time, but the idea is then that we can use tools within the cloud ecosystem to define the machines that we want to build within our project quota. One of the interesting concepts of cloud that gets hidden normally in the public context, but that we very much see in the private context is the size of it. And so people like Amazon or Azure would like to say we have infinite resources and it's as far as the eye can see. But really, in a private cloud context, we say, we have these servers, we want them all to be used. Please go and use them and don't ask for any more. So there's a very different analogy to how we make use of a finite resource here. We need to expose the finiteness of it. Just an aside, but so we talk to our cloud infrastructure using tools like Heat on the OpenStack side, or Terraform across a range of different other cloud environments. This is a bit like what it looks like. So if we want to make the infrastructure for making a Slurm deployment, for example, this is a common example, we can just codify that we want some controller nodes, some compute nodes, maybe some other bits and pieces. It's all very simple to describe. But then all we have is a bunch of servers. So we have to go through this process, this sort of codified system administration process of bringing out the Slurm packages, applying the parameters of our configuration, deploying the configuration, bringing up the services. But also, because this is a research computing oriented deployment, we want to bring in things like InfiniBand. We want to be able to bring in things like the AAI infrastructure for our users and integrate with those things. We want to bring in the cluster file systems, all of these things which take it from just being a toy snow globe kind of deployment to actually being something which we can use in a production footing. So I would say one thing though, that we're using Slurm as an example here, but you might think that means that it's an HPC environment. That's not really the point. So what we've got here is some is some data from some of the clouds in the IRIS consortium, and what you can see is that they're set up in the complete spectrum of what you get in terms of networking and tightly coupled networking. We have clouds which are at about 100 microseconds in MPI latency, which is unusable practically, and we have clouds which are at 1 microsecond. And you might think 1 microsecond, that's about what I get for my IB on my cluster, and that's because that's what it is. It is a bare metal cloud running 100 gig IB, and but it's still mediated and offered through the same OpenStack APIs. You create something which looks like a VM, it's actually a bare metal compute facility. This is one of the clouds. The main point that I want to make, though, is that while that's capable, all of the other infrastructures are set up to serve different purposes. We have machines and facilities like Dirac for providing this kind of low latency, tightly coupled batch compute resources. That's not the purpose of these machines, and that's as intentional that they're set up in a different manner.
If I may?
Sure.
I think DK published some MPI numbers on Azure, on the InfiniBand, 100 gig InfiniBand on Azure. So that's actually running virtualized environment, and they're using SRAV, so you actually can get directly to the network. And you measured 1.3 microsecond, if I remember correctly.
That would be about right for SRAV. Yep. We see the same. But I think that a lot of the clouds don't opt for SRAV because of the issues that it creates in terms of its position between performance and convenience. It's quite close to the performance side, and it means that you can't do things like live migration. So I think those are still works in progress.
Yeah, I'm not sure that they don't have it live migration, but anyway, there is no one from Microsoft here.
Yep, that's true.
Yeah. Just to say that we are. There's a program that we're running at the moment to redo the work that we did last year on measuring the properties of the big commercial clouds. So there will be more data, and I think we'll see a lot of improvement over last year. So the number that you've got here is the kind of thing that we're expecting to see.
Yeah, it is a moving target, certainly. So the project that we've been working with as one of the programs that are early adopters of Iris compute resource, and I should say I don't speak for them, I just worked with them, is the Euclid Project. And so this is a new space telescope, and in terms of what it does and its scope and ambition, it's pretty thrilling actually, because what they're looking for is to detect invisible things, dark matter, dark energy. And the only way that they can do this is by using the effects they have on light passing near them. So we're looking at gravitational lensing in the Euclid Project. And to detect something that's effectively invisible, what it has to do is see a galaxy which is beyond in the far distance and try and deduce whether that galaxy is a funny shape, so whether it has been sheared. This process called cosmic shear is caused by the presence of something very heavy in the medium ground, in the midground, which is then skewing the light that's coming from this distant object. The problem is we don't know what the galaxy looks like when it's not sheared, so they have to deduce, this is a little bit unusual, and if it was a normal galaxy it would be shaped like this. And therefore I've got this kind of distortion, which means that also there's something in between which might be like that. So there's a lot of unknowns, and it's I think that the computational challenges of what they're trying to achieve are pretty impressive. So they also think so too, because before they launch the space telescope, they have to be sure of the algorithms and the science that they have behind it. So they've been doing a lot of runs over on Euclid infrastructure, on Iris infrastructure, over the last year or so, in order to validate and prove the algorithms that they are going to be running on the real data when it comes back from the telescope. So in order to test a theory or to test an algorithm, they need about 30,000 CPU hours in order to measure the effect on a sample of 10 million galaxy images. But they have to do that, and then they have to measure the four corners around it. So they have to do another 4 runs of 30,000 CPU hours, creating this sort of 150,000 CPU hours per theory, per hypothesis that they're testing, which adds up to a large amount of compute, but it also adds up to a large amount of data. And the software stack used here assumes that we have a parallel file system, which is a very uncloud native thing to have. So astronomy pipelines tend to think in terms of a data flow kind of architecture. And what we've got here is essentially green blobs are transformations, so they're software, and grey blobs are data products. So we can see that some of the data products are accessed by many transformation processes, which then generate new data products together, which are then used as a fan out to many more transformation processes. So the way that they work with this is that they have a sort of an overseer process and a large number of high throughput jobs which are queued through Slurm, so that they're essentially sequential jobs, but they have a common file system which they used for storing the intermediate data. And so they draw products from the file system and they write them back to the file system again. And this brings up a frequent question in the cloud native mind of, well, why don't we just stick it all in S3 or object store or so? Well, that kind of is going to hurt, because without a shared file system, these jobs would need to write all their products back to object store, which means 100% of it gets transferred across the network. And then the next stage is going to have to read it back in again, which means another 100% transfer across the network. Whereas if they are in a shared file system, they have at least a pretty good chance that some of it has cached locality, and they don't have to leave the network deployment that they're in order to traverse to an object store which may be across the network itself. The second rationale for a file system was that they're seeking for portability. So they're already running this environment on conventional HPC environments, and they all provide this kind of this assumed existence of a file system. None of them provide object store. So we shouldn't really expect, cloud's meant to be the flexible one. You're not supposed to expect people to change their application in order to run in a new environment whose selling point is flexibility. So the resource allocation at the moment, we have machines at, 2 sites with a third one coming online. There are controller machines at Edinburgh University. We have some beefy compute VMs at Cambridge University, and we have some more capacity-oriented or throughput-oriented VMs at Rutherford Appleton Labs, with more hardware coming on at Manchester. But the problem we have is that there is no single way of creating a common storage between these sites. So that was the interesting area of this investigation, was how do we create a shared file system across the country. So I kind of like this map when I coloured it in. It looks a little bit like a sort of a zealot's view of post-Brexit Britain with just a wide open sea around it, but I assure you that wasn't the case. I think what we show is that there is we have hundreds of miles between the different sites, but more relevantly, we have about 10 milliseconds between the sites as well. So actually, when we look at it, this is not insurmountable. We're not looking at creating a global kind of network. It's not transatlantic. The latency and the bandwidth delay product between these different sites is actually not that big. And I'm measuring this from within one cloud infrastructure through all the software-defined router processes and back across the physical network and up through software-defined processes again. So this is the bandwidth realized at the TCP socket layer. So this raises so we've got this intractable problem, and that is, how do we manage the efficient coupling of our code and data? We can connect these sites together, but we need to think about how we're going to create what I call the illusion of proximity. So from a software point of view, the application developers aren't going to want to have to think about, oh, I'm running this in RAL, I'm running this in Cambridge, I'm running this from Edinburgh or Manchester or whatever. We shouldn't expect the programmers to need to do this. So we kind of hide 500 miles of cable by creating this open VPN mesh. So we create this point-to-point mesh between all the sites, and then we create the illusion that actually each of these sites at these different points across the country is a router hop away, a layer 3 hop. So we can expose, using these encrypted VPNs, the internal tenant networks of the deployments at each of these sites, as though they were neighbors. So I guess that this is the interesting piece for me, is that this is a problem that a lot of people are going to have, because a lot of people are going to be faced with the problem of, we have to do something in the cloud. Something has to be done making the best use of cloud environments. And how do we do that when we have data here, data there, and we don't want to throw everything into one cloud provider, so we're inevitably going to have different places, different resources connected together by wet string infrastructure. So how do we hide that from the application level so it's not painful to everyone? But how do we also exploit that so that we can make best use of it by creating tight couplings or tight affinities within one site without completely cutting ourselves off from the other sites? And that's the problem. So what we have in the Euclid deployment is essentially batch compute resource at Cambridge and RAL, stuff coming online at Manchester, controller nodes at Edinburgh, federated networking between them. And actually we create something a little bit like the sort of Conway's law model, where the software architecture kind of mimics the structure of what the application is asking for, because the first thing we do is all of the local sites draw data to them, the input data for Euclid, the trial data sets, those things, via CERN VMFS. So they pull data in via an HTTP file system, and there is nothing going across our federated VPN mesh, which we're going to be worrying about as a weak point, the wet string. So we can bring data into each of the sites independently without creating tension there. We can also make use of local scratch space where it exists, so we can exploit fast, performant, integrated resources. And in a public cloud context, that could be, elastic file systems within the cloud environment itself. But in, for example, Cambridge University's case, we can make use of local Lustre storage, which is only visible within the Cambridge deployment, but it serves as a local scratch. But what Euclid want is a single global multi-site file system. And so that's where Seth comes in. Now Seth is essentially sort of a file system for OpenStack environments and other sort of multi-node distributed storage clusters. It's not the fastest, but it is very flexible, and it is quite resilient, and generally doesn't go wrong too often. So it's quite easy to use, quite easy to set up, and it provides good functionality. What we can do is, with Ceph, we can support this idea that we have local storage or local access, and we have a global namespace at the same time, which is the kind of the inherent contradiction of this multi-cloud problem. What we can do is we can create an environment in which we have storage from the Cambridge deployment, storage from the Rutherford Appleton deployment, and we can access that locally from each of the sites by the compute nodes local to that site. But when they wish to see the files from the other side, they also see those files, and then that data is delivered from across the VPN. But the way that works is that we have, inside a Ceph file system, we have a number of storage pools that back it. And we provide a metadata storage pool, which is global. And then within subdirectories within our file system, we can actually bind those to local storage. So that if I'm mounting my file system in Cambridge, and I access a subdirectory, which is the Cambridge subdirectory, I can guarantee that the data is going to be served from machines that are local to me. I can still see the data from the RAL directory, but I know, because that's what I know, that data is coming across the country to me. So I will be able to get it, but it will be painful. And that creates this nice kind of trade-off, really, in that we have this illusion of proximity, so that when we want to do things like have a home directory which is visible to everyone, we can use the combined resources of all of our deployments. But when we want to access data which is local, we can do that and guarantee that within the same file system, on the same storage, and it growing and managed as a single entity. So we could easily add a /Lester on the end of here and bind it to local resources within this university if it was part of the Euclid deployment. So now we've created a machine which has a global file system which is spread across multiple sites. And that brings together a kind of the complete package for this particular software platform, the Euclid as a service environment. So we've got a Slurm environment for doing the batch queue. It has Euclid software in it as well. We've extended it with a bunch of packages. It doesn't particularly matter what they are, but they are custom to the Euclid application requirements. And we bring in these additional services and so on because we can define these in a cloud-native context. The end result from a system in Edinburgh University is a Slurm queue with 3 partitions, and those partitions then are implicitly scheduling compute nodes to particular data areas within the Seth file system and particular regions within the country. So now what we've created is a locality-aware global cluster. Obviously, this is somewhat experimental. These are ad hoc file systems for transient data. So they don't provide, it's not the way that Seth would work normally, and it's not really for a production long-lived deployment. But for the duration of our test runs, this is how it works, and it seems to be working pretty well. Obviously, we knew that the software-defined OpenVPN mesh is not really a suitable candidate for large-scale bulk data movement, and our telemetry has proved that. So I can go through some of that. But first of all, it's worth emphasizing actually it's working, and it's working right now. Has been working for several months at this scale. And what we've found is we've got several million of these data flow Slurm jobs through our system. We've had some teething problems, so Seth tends to grow in its memory consumption to the point where all resources are consumed and nodes get killed, and that's normal. But the interesting one has been how Seth itself has performed when it's running consistency and cluster membership protocols across a national network. The VPN tunnels can be a bottleneck, but actually what we found is that they're not normally a bottleneck. It's actually performing very well because the application has been structured to use the local data. We can create gigabytes of aggregate throughput, but only megabytes across the VPN itself. So we don't actually overload the VPNs. So I can show you that here. So what we have here, these are graphs from Prometheus Telemetry, which is monitoring the Ceph cluster. And Ceph is actually very good at providing sort of white box data about what's going on inside it. The top row is the sort of the user-facing protocol, and the mean commit time for an object to or a file to a Ceph cluster on this machine varies according to load, but it's typically around the sort of 20 to 50 millisecond commit time. But then on the lower level, we can see what's happening with the local disks and the local storage, and it actually is sort of half a millisecond or more. So we can see between the discrepancy between those, that creating a federated file system with a largish ping time between them creates this inherent delay in committing data. And for a Ceph being strongly consistent, that inevitably could be sluggish for progress. The machine itself, so the cluster deployment, it goes up and down in terms of the overall level of utilization. We typically see between 500 megabytes a second to 2.5 gigabytes a second of overall throughput. But at that time, the VPN cluster, which is the top right window here, we're only seeing sort of 5 to 20 megabytes a second going across the VPN, which is not overloading it. And that's interesting because we've been looking in good detail at where the back pressure is coming in on this multi-cloud deployment. We knew that it was going to be a problem for the VPNs, but actually what we found is that the VPN itself is performing pretty well. On aggregate, the load on it is not particularly high. We see occasional packet discards on the tunnel endpoints. This bottom right graph is something that we added, which is if we sum all of the unsent data in the kernel TCP stacks across the deployment, what does it add up to? And this is then a nice metric which gives us an instantaneous snapshot of back pressure. All of the unsent data on one half of the cluster or on the other half of the cluster. And we can see that it spikes to maybe a few megabytes of unsent data across all of our nodes, but it's never actually grown to be a substantial problem. However, we do have interesting problems with Seth's cluster membership protocols, and this comes down to QoS, and it comes down to traffic shaping, and I think it comes down to microbursts of congestion. Our sampling period for these is about sort of 10 seconds. So every 10 seconds is real coarse granularity for network congestion. We wanted to be able to see things going on at the sort of the microsecond or millisecond level, and we just don't have that level of precision here at the moment. So in summary, we've got a nice kind of functional design here without being a particularly performant design. It grows with the deployment. So our Slurm cluster, because it's cloud deployed, it can grow and shrink. We can increment and decrement overnight, take servers away, add new servers, and the file system grows and shrinks with it. We have a nice proximity sort of presentation to the users. And if they know about this and they are wise to it, then a savvy user can make use of local storage and exploit local storage where they can. And there's a clear pathway here from this system to a system where the infrastructure is adapted to suit having these high-performant tunnel links between the different sites, either through reconfiguration of the cloud infrastructure and the networking of it, or through throwing some hardware at the problem. So the next steps, we've got some pretty good instrumentation at the moment. All of this is open source. But I think we can take this further. We can really get to understand where the extremis is, where the tension is in a multi-cloud deployment and the networking that we're laying over it. Our Seth needs a bit more constraining on the management of its memory consumption. We're going to be using traffic shaping to pick out the near real-time protocol requirements across the VPN and prioritize those. And also we're going to restructure the way that Seth is working so that not only the data movements are kept local, but also the metadata service for each of the directories is kept local as well. Essentially decoupling the file systems a little bit without actually taking away this presentation of a global resource. So everything I described is online and is freely available. It's all open source, and you are welcome to use it, particularly if you feed back. So, thank you very much.